Hi, I am Tianlin Zhang from Harbin Institute of Technology, Shenzhen. In this presentation, I'll talk about our work, Dynamic Object Tracking for Quadruped Manipulator, with Spherical Image-Based Approach. The Quadruped Manipulator is a multifunctional platform that is comprised of a mobile quadruped and a manipulator. It has not only the agility of the quadruped, but also the interactivity of the manipulator. In nature, animals often show their skill in tracking dynamic targets. For example, dogs are good at tracking flying frisbees. Faced with such dynamic targets, they rely on their senses to coordinate their motion. This makes us think, can we develop an approach that enables the quadruped manipulator to autonomously track dynamic targets, using only RGB images? We use image-based visual servoing, IBVS, as the approach to achieve this goal. However, employing IBVS for the quadruped manipulator has at least three challenges. The first challenge is dealing with the coupling motion between the locomotion and manipulation, which requires the IBVS to consider the full system states. The second challenge is caused by the under-actuation of the quadruped platform. When the robot is under a dynamic gait, like trot, the roll and pitch angles of the quadruped platform are uncontrollable, which affects the operation accuracy of the manipulator's end effector. The third challenge is estimating the target's velocity without depth estimation. To track a dynamic target for the quadruped manipulator without depth estimation, we propose a novel IBVS approach that consists of three parts: a spherical projection model, a robust super twisting observer, STO, and a model predictive controller, MPC. First, by projecting the images of the dynamic target and the manipulator onto the spherical image plane, we build a visual error equation with the passive-like property. The passive-like property allows us to separately control the position and attitude of the quadruped manipulator, so we can avoid the attitude of the quadruped platform affecting visual error convergence. Then, with the spherical projection model, the multivariable STO is exploited to estimate the target's velocity without depth estimation. Finally, MPC for the quadruped manipulator, based on the single rigid body dynamics, is used to generate joint torque. Now let's take a look at some simulation results, where we compare our proposed approach with other methods as the baseline. The experiments were conducted on a quadruped manipulator consisting of an AlienGo, a 6DoF Canova Gen 2 manipulator, and a D435i RGBD camera. Notes that only the RGB images from the RGBD camera were used. We want to compare our approach with the baseline method, a spherical model without STO. The target's velocity was set as 0.3 meters per sec. From the videos, only our approach successfully completes the tracking task with the help of STO. Then we look at simulation results for a tracking task where the target velocity was set with changed velocity. From the videos, the STO can accurately estimate the target's velocity, and our method can successfully track the target. Then we look at simulation results for a tracking task where the target was set with an S-shaped trajectory. From the videos, our approach can also successfully track the target. Then, we look at experimental results for grabbing a household object, teddy bear, to finally validate our approach. The feature points of the target were obtained by YOLO, and the target's velocities were set to 0 meters per sec and 0.1 meters per sec, respectively. From the videos, we can see that our approach made the robot produce coordinated motion, where the quadruped is constantly adjusting its position to help the manipulator successfully grab the target. In this research, we discussed an opportunity for the quadruped manipulator to track dynamic targets only using RGB images. To achieve this goal, we proposed a novel spherical image-based approach. The approach considers the full state of the quadruped manipulator, which enables simultaneous locomotion and manipulation, and the approach also builds a visual error, with passive-like property to eliminate the influence of the under-actuated quadruped platform. Then STO is designed to obtain the target's velocity without depth estimation. Combined with 2D detection methods, our approach can be used in various application scenarios, greatly improving the quadruped manipulator's autonomy. Thanks for your attention. If you have any questions, you can contact me by email.